right, let's look at some example problems. So here I have this system, ABC matrix. My D is 0. I'm going to define this matrix T. So the determinant of this is non-zero, and so I can take the inverse of this. So this matrix inverse happens to be this. And I can go through and do my similarity transformation. A tilde, B tilde, C tilde. So in this case, notice that I end up with a diagonal matrix. And so my original system then gets transformed into this system. Clearly a simplification in doing so. So this is the process that we would go through of working with this. In our second example, I'm going to look at an A invariant subspace. So here I have this matrix, and here I have a couple of vectors that I'm saying are an A invariant subspace. So I've defined now a matrix from that subspace, and I take A. And so it can be shown that A S naught is equal to S naught M, where M is given by this formula. M is given by that matrix. So we have an A invariant subspace. So if I take this matrix now and compute eigenvectors from it, I can go through and compute eigenvectors for so V and W, such that AV is equal to V times capital lambda, and M times W is equal to W times C. Okay, so these are the two diagonal forms that we have for A and for M. We have the diagonal forms. So I'm going to define S tilde to be V naught inverse S naught W. In this case, it happens to be this. And I can go through and show now that lambda times S naught minus S naught tilde minus S naught tilde times psi. Okay, so notice this is the lambda, this is the psi, this is the diagonal form of A, this is the diagonal form of M. And I can go through and show that this difference is equal to 0. That is, this quantity is equal to this quantity. So we have that kind of relationship. So we can go through and show, so notice that this diagonal form and this diagonal form have eigenvalues in common. That is, in this case, I have this Jordan block that appears down here. So the A matrix, the original A matrix, has additional eigenvalues that do not appear in here, but these eigenvalues do appear in here. Okay, and that's all that this is saying. Okay, we have that in common. Now, we're looking for something like this: A S naught is equal to S naught times M, and as I mentioned, in general, we're going to be having M of dimensions smaller than A whenever S naught comes from a basis. But if we choose something that's not a basis, we can get something like this for larger matrices. So for this S and for this M, I get this matrix. And we notice that this M, first of all, is not diagonal. Okay, and that's mostly because this matrix is not eigenvector matrix. But it satisfies this relation: A times S is equal to S times M. So in this case, S is big, M is big, but I still get this relationship happening. And we'll come back later and see where something like this can actually arise in practice. So an A invariant subspace is important to have as a tool in our toolbox. We won't use it very often, but when we need it, it's going to be handy. So that is some work practice problems.